So I guess we'll start. So I'm Vincent Reverdy. I'm working at the University of Urbana-Champaign. And today I want to talk about what kind of tricks we can do with C++17 and C++14 and 17 to make truly generic interface using SFINAE and using lambdas. The goal being to make SFINAE easier to use and the code far more easy to read. So once upon a time, I was working on cosmological simulations, simulating galaxies, how galaxies form, etc., etc. And to do high-performance numerical astrophysics, I investigated template metaprogramming. So it was back in 2011, and I was discovering template metaprogramming, and I was playing with it a lot. So the good thing that it was that it was leading to great performance and great genericity. The problem is the kind of thing that I was writing back then. I was all excited, but the problem is that it's completely unreadable and completely unmaintainable. And then I realized that no sane human can read my code. Although the code works great and delivers amazing performance, it's modular. The problem is that it's completely unmaintainable, and the minute you need to dig into the details, I mean, you can do nothing. That being said, the code I just showed is still working as a production code and is still running on supercomputers. However, 6 years or 7 years later, I learned how to write better template metaprogramming code, and the C++17 standard has been published. And it allows new things to be done, and I will try to summarize them in this presentation. And currently now I'm working on a generic tree library to be able to handle both cosmological simulations, but also some kind of machine learning algorithm. The main question I am asking is how can we write a super generic tree library in a very readable manner? So this presentation is about how can we improve the genericity in C++17 without paying the price of code complexity and code readability. I want to focus on 4 particular things. The first one is that I want a black box that, as an input, ask whether something is compiled, something is valid code or not, and if it is valid code, then it will do something. Second black box is that you give the black box a list of functions and a list of arguments, and it calls the first function compatible with the given arguments. Third thing, you give the black box a list of functions and a list of arguments again, and it calls the best function provided for the arguments that you provided. And last thing, you give a list of types and a list of expression, and it will pick the first type that leads to valid expressions. And I want to do all of that directly in the code without writing a lot of boilerplate code. So all begin with substitution failure is not an error, SFINAE. So I guess most of you know what SFINAE is, but just in case you missed something, so substitution failure is not an error, refers to a situation in C++ where an invalid substitution of template parameters is not in itself an error. According to CppCon's reference, there is also this definition, and it's also defined in the standard as if a substitution results in an invalid type or expression, type deduction fails. An invalid type or expression is one that would be ill-formed with the diagnostic required if written using the substitute arguments. Only invalid types and expression in the immediate context of the function type, its template parameter type, and its explicit specifier can result in a deduction failure. So the example provided on CPP reference is the following. So you have You have several overloads of the same function, and you constrain the function by the return type, so that the overload selected will depend on whether this expression is valid or not. And so you have this version, and when you execute it on x, reference of x, and 42, then you call the three different versions of the functions, which is cool. Then the other very classic example is enable if, so I guess everyone knows it. It's just to constrain using parameter template types what overload you will select. And using that technique, you can, if I say here that this function is only valid if t is an integral type, and here if t is a floating point type, then when I call the function, the first one, when I call it on an integer, it will call the first one, and the floating point, it will return the second one, etc., etc. And then in C++17, there is a new tool to play with SFINAE. It's void t that allows to do the same kind of tricks, but far more easily on class types, on template class. So, for example, I want to check whether a type is iterable or not. So I have the default default definition of is iterable. And then I use the void t to say that this type will be more specialized if I have begin and end that can be executed on t. And using that technique, if I call is iterable on vector, then it returns true. Same thing on map, but on a double or on this data structure, it doesn't work. It returns false without the code crashing, without the compiler crashing. So SFINAE, enable if, and void t are amazing tools for all sorts of metaprogramming tricks. The problem is that sometimes it requires a lot of trickery to make it work, and it's not very expressive in the sense that when you read the code, it's not immediately clear what the original developer wanted to do. And also, it leads to a lot of boilerplate code because for every trick you need to do, you need to implement a new function or a new class. The good thing is that concepts will solve some of these problems, especially with the enable if, but SFINAE will remain useful in a lot of situations. So wouldn't it be great to be able to write inline SFINAE without extra boilerplate code? That's the question I'm asking, and this is what I will try to do in the rest of this talk. Also, there are some non-trivialities with SFINAE. For example, here, so we have a trait that contains a type, and check, and the type is equal to the parameter t, dot type. Okay. Then I have a function, I have a function immediate context, and I have a function non-immediate context. The difference between immediate context and non-immediate context is that the first one check whether the type is available directly on t. The other one is checking through the trait data structure. And then I just have a structure that happens to have a type. So when I call the immediate context function, it compiles when I call it on an integer or on the structure. But with non-immediate context, when I call it on the integer, it doesn't work. And it returns the following error message in G++, error int is not a class, strict or union type. And if we come back to the definition given in the standard, the reason is that SFINAE should happen in an immediate context. So when you have to deal with this kind of trickery, it's not always easy to avoid this situation or to know why your code was not able to compile. A thing that we can use SFINAE for is, for example, to implement a ranked overload set. By that I mean you have a list of functions and you want to try whether they work in a given order. A way to do that, so the thing I want to illustrate is the following. So we want to create a function element count so that if t has a size member, then it will call it. If it doesn't have a size member, but it has begin and end, or begin and end works on t, then it will call std distance and begin and end. And then otherwise, it will assume that t has only one element and returns one. And the trick we will use is that non-variadic template parameters are always preferred against variadic template parameters. And we can use this trick recursively, actually. So first we start by implementing a function container element count. The first version check whether it has a size member, a function member. If it has a size function member, then it returns it, and the other one here is using distance and checking whether begin and end are compatible with the type t. And here what we do is that we use the variadic template trick to have the compiler check first this instance and then check this instance in second. And then if we do the same trick now on element count, then now what I want to do is that I want to check whether container element count can be called on t. In that case, it means that either it has a value member or distance can be called. Or if it doesn't work, then I want to default by returning 1. Again, by using the variadic template that will be the least preferred option. And when we compile this code, then when I execute it on 42, it returns 1, because there is only one element. On forward list, it uses std distance. On vector, it uses size. And on initial other list, I have a specific overload. So it works great. But it required a lot of code to make that work. Another trick that we can do is to use an overload rank to have the same behavior. So we define this structure, overload rank, that recursively inherits from an overload rank with parameters that is with the preceding integer as a template parameter. So for example, overload rank of 1 will inherit from overload rank of 0. And then we re-implement the element count. So in that case, what we do is that I have the 3 versions. So the default, the more refined version has an overload rank of 2. In that case, I call size. If it has an overload rank of 1, I call std distance. And by default, I returns 1. And I use this thing to call actually the right overload by appending overload rank of 2 at the beginning, so that it will first try the most specialized version. And if I execute it again, the first one will call overload rank 0, second one overload rank 1, and then 2 extra. So it works, but again, that's a lot of code to achieve something pretty simple. So as I said, SFINAE has all these good properties, but the problem is that it's not really evident to see what the user is trying to do, what the developer is trying to do, and also it's not straightforward to use. So wouldn't that be great to be able to write inline SFINAE without extra boilerplate code? So we will see how we can do this. So what we want to do is that we want to be able to do the following. To check whether some code here compiles, so I use a ifconst_expr in C++17. I want some black box that tells me whether x size compiles, and if it compiles, then I want to execute this function. I want to set count to x.size. And then if this one was not working, but std distance is working, then I want to call that, and if not, I want to set count equal to 1. The question is, what should the black box be? So here, to be able to solve this problem, there is an interesting observation to make about lambdas. So let's say I have this checker function that just you give it a function or a set of callables and arguments, and it will check whether the function f will be invocable on these arguments. If it's invocable, then it should return true. If not, it should return false. And then I call check on two lambdas. The first one is x.size on 42 and x.size on vector of int. So the first one shouldn't work, the second should work. If I do this, then I have compilation error. Of course, because it's trying to, there is no SFINAE here, so it fails and the compiler crashes. Now let's try something else. Let's try to deduce the return type by writing decal type auto as the return type. If I do this, so the only change between here and here is decal type auto. If I do this, then same thing, I still have an error. Now let's try a third thing. Now I set the return type of the lambda to decal type x.size, and I run it, and now it works. So if I want to check whether some code is viable or not, I can see how I can use this trick. And it works even if the lambda is completely empty, if I just use the decal type. And there is no warnings, there is nothing, it just tells me that the first one was able to be executed on the argument, the first one was not able to be executed in 42, but the second one was able to be executed in vector. Great. So if we want to build, so the general idea is to make the thing a little bit more generic. Instead of returning a bool, we can use the same trick to return true type or false type. So I use again the same trick with an empty lambda, but in that situation, the function check, the only difference is that the check has changed of definition, and now it returns a type that is different depending on whether the lambda is invocable or not. Again, it returns false and true. So if we want to build, so this trick works. If we want to build a library that gives the user plenty of options, then we can build it that way. So first, we will create a class called validator. And so here it's just helpers, nothing important here. But you create a validator and you give the validator a set of functions, a list of functions. And here is just checking whether the functions you give to it are the same type as the callables, can be converted to callables. And then you have the function call operator that is exactly the check function we had before. So it returns whether the function is invocable on the thing. And then we can define a detection guide so that I don't have to specify by hand the callables parameters and a few helper classes. Then from validator, I create a validate function, and what it does is basically the same thing as the check function was doing, except that now it checks whether a list of functions works. So I have a set of arguments and I have a list of functions, and validate will return true if all of the functions can be executed on the given parameters. And finally, I can create an isValid class. And here I will use a trick that can be done in C++ 17 with template deduction guide. So first, I have my generic version of isValid. IsValid, you give it a list of arguments, and you build it from a list of functions. Okay? And it will set a value to true or false depending on whether the callables can be all called on the arguments. And so I have a constructor from callables and constructor from validator, and then an implicit converter to Boolean. Then I have another specialization of isValid, and this time isValid takes a list of arguments again, but this time isValid is built not from a list of functions, but a list of arguments. And there is a caller, a function, an operator parenthesis, where you give it a list of callables. And it returns the same thing, the same trick as check before. It will check whether all the callables can be called and the arguments. And this time I have a template deduction guide that says that whether if you build it from a list of arguments, then it will create the class, the specialization valid and arguments, void and arguments. What this thing allows to do is to detect, having these two specializations, allows to detect whether you have specified by hand template parameters or whether the template parameters should be deduced. If the template parameters are deduced, then it will call this version. If the template parameters are not deduced, it will call the previous version, which is this one. And then I have these nice functions, and I can easily call them on lambdas with arguments. So validator, you give it a list of lambdas and an argument, and it will return whether the thing is valid or not. Validate, same thing except you give the argument as a template parameter. So, and then you give the functions. And isValid can be used in two different manners. The first one is by explicitly saying what the type of argument should be. So in that case, int and vector of int. And then you give it a list of lambdas. Or in the other case, you don't specify the template parameter, but you let the deduction guide deduce that here it is int and here it is a vector. And it checks whether the lambda works or not. And with isValid, we can even do more complex. So by the way, this trick is only working on Clang for now. It's not working yet on J++. J++ is lost with the deduction guide trick for now. But I think this should be resolved soon. So we can do with isValid, as I was saying, we can do more complex statements. For example, by trying to see whether the type you provide leads to a set of valid expressions. So in that case, it checks whether int can be replaced in that expression and in that expression, and returns true if both conditions are met. Or you can even call it on a list of types. So is it valid to replace int and vector of int in both of these lambdas? And the good thing is that finally, the thing we wanted at the beginning, we can do it. We can write if context per, if this type t, that is the input parameters, have the function size, then I call size on x. Else if it has begin and end, then I call distance, and otherwise I'll just return 1. And now I don't have to define extra functions or extra boilerplate code. It works as is. It's inline SFINAE in a sense. So cool. Then let's try to do other trickery. And for example, let's try to create overload sequences. That would help in certain situations where you would like to branch to the first function that would work. So the goal is the following. You give a list of functions and a list of arguments to a black box, and you want to call the first function that is compatible with the arguments. So the goal is the following. There should be some black box, f, to which you give a list of lambdas or a list of invocable things, invocable objects, and it will try to give the argument to the list of functions And the first one that compiles will be called. So in that case, if you give it 10 and 42, it will try the first one, it doesn't work. It tries the second one, it doesn't work. Then if you give it 10 and 42 in that expression, it will work. So it should return 52. How can we do this? So we will use the same kind of trickery as we did for inline SFINAE. So first, we will define a helper struct that is just index constant. This is just an alias for integral constant of size t. And then we will define a helper struct, tuple index. And what tuple index is doing is basically, so you have a tuple of types, and you search a type within a tuple of types. And it will return the index of the first, type that is equal to one type in the tuple. So for example, if your tuple contains int double string, and you call and you use tuple index on double and your tuple, then it will return that the double was at the second position in the tuple. But so index would be equals to 1 because we start at 0. Oops. So the tuple index. Yeah. So tuple index, example of use, if I call tuple index v on int double double with int, it should return 0, and if I do the same on int double double, it should return 1. It returns the first type that is equal to one type in the tuple. And it can be used on a sequence of Boolean constants. So if I have a sequence of false type and true type, then it will also work. And as a remark, the same strategy could be used not on a tuple, but an integer sequence of Booleans. So now if I want to find the first invocable function, here's what I can do. So I declare an overload sequence that will be a class that will do all the trickery. Then I create an overload sequence selector, and what the overload sequence selector will do is that you give it, an overload sequence of callables and a list of arguments. And what it will do is that it will create a tuple of, this thing will create a tuple of true types or false types depending on whether the callables are invocable on arguments. And then I use tuple index v to find the first invocable function that works on the arguments. And then I have some helpers functions. And then the last thing to do is to create my overload sequence. So just few helpers, and then what I do is that I have a constructor that can be constructed from a list of functions. So you give it a list of functions, it will return you an overload sequence. And then you have a call operator where you give it the arguments, and it will, what it will do is that it will use the overload sequence selector to pick the first one that works. And then I just have a deduction guide so that overload sequence of uncallables creates an overload sequence of callables. And finally, I need the last thing, which is type t. So it's just an alias that is a little bit more generic version than void t. So type t, just you give it a template parameter pack of arguments, and it will just give you the first type. And void t could be redefined as type t of void and a list of arguments. And now let's go back to element count. So now, using overload sequence, I can create an overload sequence element count. And what I do is that I give it 3 lambdas. So the first one, the return type is x.size, and it will execute if x.size works, then it will call .size on x. Then I use type t to say that my return type will be size of t, and then I check whether there is a type std begin of x that exists, and whether the function std_end can be called an x again. And if that works, then I call distance and an x. And then by default, I return 1. And this version of element count works because now if I define element count like this, then if I call it on vector, it will try the first one, it will work, so it will use dot size. Same thing for forward list. Then it will use std distance, and same thing for an integer. So now that's great because I don't have to do the trickery I did in the first part. I can just define my overload sequence with a set of lambdas or set of functions or set of invocables, and then I just call it on the arguments, and it will pick the first one that works. And from that, with the same idea, we can build a set of tools with the R and no throw version that relies on the different version of invocable, and also forwarding overload sequence that will call the callables as qualified at the construction, contrary to the callables as qualified on the call side, And I have also the three helpers, type T overload sequence selector, and invoke result will work without problem on overload sequence. And to wrap up now, I can solve the original problem I have, and I have my black box that is called overload sequence, and I define my set of lambda, and surprise, it returns 52, without having the need to define a lot of functions independently. Great. Now let's try to do the same with overload sets. So overload sets, I give it a list of functions and a list of arguments, and I want the black box to pick the best thing according to overload resolution. So the goal would be the following. I give it a lambda. I have this magic function, magic thing f. I give it a lambda that can be executed on int, a lambda that can be executed on double, and a generic lambda. And if you give it 10 dots, then it should execute the second one, because this is the best fit according to the overload resolution thing. This one is easy. So you define your class overload set that inherits from the callables you give it. And you say that you move the operator, you promote the operator equal so that it's visible from the overload set. And you build it from a set of, you can build the thing from a set of callables, a list of callables. And you have this execution guide so that everything works fine. And then again, you can design a family of tools, overload set, forwarding overload set selector, and invoke results. Great. Problem solved. You execute overload set on the three lambdas, and this one should return 1, will return 1 because it does x divided by 10. Great. Wait, really? What about non-lambda classes with an operator equal? You can inherit from them, so it's fine. Now, functions. Problem with functions is that the trick I used for overload set inheriting from the set of callables won't work here, because I cannot inherit from functions. However, I should be able to wrap them in a class. What about pointers to member functions? Reference to qualified pointers to member objects that are invocable things. Reference to classes, so with an operator parenthesis. Final classes with an operator parenthesis. So the thing on final classes is that I cannot inherit from them. And what about unions with an operator parenthesis? All these types are invocable, but apart the first one or the other won't work with the trick I used. And if we take into account all of that, then overload set becomes a total nightmare. And to give you a glimpse of what kind of nightmare it is, there are two things we should clarify. First, how to make forwarding classes in C++ 17 using template deduction guides. And then what is a callable exactly? So moving to forwarding classes. So this is a forwarding function in C++11. So it just takes an f and a list of arguments and just calls it forward f and calls it on the list of arguments. In C++14, we can use decal type auto and it works fine. In C++17, we can do the same, but we can use invoke that is more generic than the previous ones. Great. The question I want to ask is how to do the same with a class. A class that would be a caller that would be built from f and then called a list of arguments. So to see what the problem is, let's try to see what happens if I have the following. So I define a structure, and the structure is built from urefref, an X that is qualified as a universal reference, and I build the value from U, from the X that is forwarded. And then I have decal type auto of operator like this that will return the value, and an operator of int, it will forward the value. The question is, what types are A1, A2, and B1, B2? So let's say the deduction guide is urefref to U. Then what should be A1 when I call this first function, and what should be A2 when I call the second function? And same question when I do urefref here and it deduce urefref instead of U. And this question is not so trivial for most of people. So to try to answer this question, we can try all the options and see what comes from it. So to be able to do that, there is a trick that works on GCC and Intel and Clang, and on Microsoft there is another version. You can define a print type that will just call this macro, and it will print the type of your parameter T. Great. And then you can start experimenting with all the types and all the conversion that can happen. So let's say I define a struct type, and I will use T as defined as type, a reference to type, double reference to type, const type, reference to const type, and double reference to const type. And the question is, what happened for T, what happened for tref, what happened for trefref, which means trefref is what you have as input here, and you put refref after it. And you can study all these conversions happening. And you can do, as I said, you can try a lot of things, see how forward will forward, see how decal val works, and all types. So this presentation will be posted online on GitHub, but I have all the conversions for all kinds of types. From that, we can deduce that all of these things are basically the same and results in the same kind of type deduction. For all of these, for T0 to T9, regardless of the input type, you will always get the non-qualified type. Same thing here, the two are the same by using decal val, and you get that as the output, and same thing for all these types. Great. What I want to say here is that given the original structure I had with this trickery, now we can answer easily the question, because we can go in all the tables and see what were the conversions that were happening, and then we can deduce that here it was int, it was int double reference to int, here reference to int, and here double reference to int. So they're not the same. And let's say we have this structure. So the structure has a template parameter type class T, and I have a constructor from U here. One question we can ask is whether the template deduction guide should be this option 1 or option 2. Should I put U here or urefref? And as a remark, when you call this operator that just does decal type auto and st forward, the return type of both of these versions will be the same. What we can do to try to answer this question is use a reporter class. So I put the link to the GitHub. What this class is basically doing is that it tells you all the conversions that are happening. So for example, if I create all these reporters, they will tell me all the things that are happening about their creation and the kind of functions that are called. Therefore, for debugging the conversion and types, it helps a lot. So now let's try to see what happens with option 1. So option 1 leads to that, and option 2 leads to that. The important thing to notice here is that so you have all the construction, all the calls of operators, and all the destruction. And here you have the memory, the address that is used by this reporter class. And if you call an operator on something that is already to 0, then it means that you have a memory leak. And in that version, we don't have memory leak. All the operators are called before the thing are destructed. But in that case, here I called this operator while the internal pointer was on 0, which means that this version will leak. So you should not use this type except if you know exactly what you're doing. You shouldn't use this version where you deduce urefref from urefref. The nice version that will work most of the time is this deduction guide. So great. That will use a lot to create this overload set. Then the other question I ask is, what is a callable? So according to the C++ standard, a callable is basically something that can be called on some set of arguments by invoke. Great. The question here I want to ask is, in practice, how different categories of callables exist? So let's try to list them. So first we have this, which is just a function. It's a basic function like f, so it has a return type and a list of arguments. Then you have this version, which is the variadic version. Not template variadic, but variadic function. Then you have, since C++ 17, the no except is part of the function signature, which means that you have these types. Great, we have 4 types now. What about qualified function? So function that comes with the qualifiers after that. So you shouldn't be able to write this, but if I have something that extracts, that can be executed in a function, a class member, and removes the class and get the type, then you can have qualified function types. Which means that you have all these functions now, all these different types. So the first one are the regular qualified functions with all the types of qualification. Here it's L-value reference to function, then R-value references to function, then function pointers. And then, so I have, as I said, all of that, and all of that, it's already a lot of types. So for example, you have things like ref const volatile double thing of args. And you have 48 versions, the 48 version, qualified version I showed before. And then you have the same thing on function pointers, member function pointers. So already, if you compute everything, you had 720 function types for the first one and almost 600 for this one. Then you have member object pointers, which are also callable and usable with invoke. So again, same types of things. You have an extra 144 types. Then with closure types and class types and struct and unions, we are already at more than 1,000 different function types. And all of these things work with std_invoke. And for example, it works also if I have weird qualified reference to classes. Great. But this is not all. C++ is never that simple. So I won't go into the details, but what this thing said is that if you have a class if you have an object that is convertible to a function pointer, then it's also invocable. For whatever reason that I don't know, it's not valid on member function pointers, but only on function pointers. So a callable type can be all of this, in summary. So a function, reference to function, or pointer, or reference to pointer. Same thing for member function, same thing for member object, then closure, class, struct, union types, and then things that can convert to the first thing. And this is in total almost more than 1,500 forms of types. And the standards define all of this. All of this is defined in the standard. One interesting thing is that a function object is not what we would expect. A function object in the standard is not an object with an operator parenthesis. It's either an object with an operator parenthesis or a pointer through function. Great. So now we can come back to the overload sets. And how can we use all that information to make overload set works? So in P1016R0, I am defining a lot of helper traits that have been proposed to the C++ committee in the library evolution working group for now. And basically, it just extends the possibility of type traits by, for example, allowing you to copy qualifiers, or to check whether you can inherit from something, or to check whether a type is a closure, a functor, a function object, or a callable thing. And with the help of these traits, I can promise you that it becomes possible to actually write the overload set class. Except for two things: for final classes that are not inheritable, and except for unions that are not inheritable either. If you want to try to implement this thing, you can. As I said, I promise you that it works, except for these two things. The thing we can hope is that with C++ reflection facilities, we will probably be able to finally do it on final classes and unions. And then the last thing I want to talk about is playing with types. For now, we played with functions. We check whether some code was valid or not. The last thing I want to do is to provide a list of types and a list of expression, and to check whether the expression, when you put the types in the expression, it works or not. And what I want to be able to do is to check, like to pick the type corresponding to int, if that works. If it doesn't work, I want to pick the std vector of int. If that doesn't work, I want to pick double. And here, I want to put some lambda trickery. So once again, we use the same kind of techniques illustrated in isValid and overload sequence. So first, I create a tag invalid option. Then I have this first function called type option. What types option does is that you give it the type that is not deduced, so you should give it explicitly, and you have a list of lambdas. And what it will try to do, it will check whether all lambdas can be called on a parameter t. And if it's not able to call it on a parameter t, then it will give invalid option. And then I have another function, type selector, where I use the trick with the tuple index. Again, same thing as overload sequence. And what I'm basically doing is that I am trying to check what options are variable or not. And I can use it like this. So I define a lambda that checks whether the type has a size. And then I have my type selector where I have first int, and I want to check whether the lambda can work on int. And then I have a std vector of int. And same thing, I want to check whether it works or not. And I want to return either int or vector of int, depending on the first one that compiles. And if I print the type, hurrah, here in that case, it gives us std vector. The only problem that for now, you cannot declare lambdas in unevaluated context, which means that I have to write explicitly the lambda and then call the thing in lambdas. It would be great if we could declare lambdas in unevaluated context so that this trick could work by defining directly the lambda here. And then that solves the problem. We have this magic function that is called type selector, and I can call it on things and returns the first type that leads to a valid expression. Great. So in conclusion, the main question I was asking is how can we improve code genericity without paying the price of code complexity and readability? I showed 4 different things. Something that check whether an expression compiles or not and returns true or false depending on that. Then an overload sequence that will pick the first function or the first callable that is callable on a list of arguments. An overload set that still doesn't work for 2 categories of functions, but you give it a list of functions and a list of arguments, and it will pick the best according to overload resolution rules. And then a type selector that allows you to do the same kind of tricks as with overload sequence, except this time not on functions, but on types. And coming back to the beginning, now by using all these techniques, it simplifies a lot when I want to write super generic code, and checking the properties on types, and depending on the properties of types, I want to make decisions. For example, let's say you have a set of algorithms with different scaling capabilities, and I want to pick, depending on the complexity, I want to pick at compile time the best one. According to this, I don't have to write a lot of functions, a lot of boilerplate code. I can just use isValid or overload sequence to do this. In this talk, I have introduced a lot of different classes and tools. They are summarized here. Some of them can be found in the proposal P1016. All of these things are somewhat related to what I just showed. This work has been made possible thanks to a number of people, organizations, and institutions. And thank you for your attention. And all the questions are welcome. Yeah. Yeah.
So firstly, I'm impressed by your rigor on checking out the combinatorics on that sort of problem. Your implementations generate quite a few types under the hood as part of these instantiations. Have you benchmarked the compile time resources you're consuming for doing this relative to a library like Boost HANA's isValid or Boost HANA's overload or overload linearly?
So I didn't benchmark. I looked at what Boost HANA is doing, but I didn't benchmark yet. But this is definitely something to do.
If you want some help benchmarking, I'd be happy to help.
Great. Yeah. If no other question, then thank you.